Here's the exercise. We need to find the input and output resistance of the circuit. When we calculate the input resistance, the output port should be opened. That is, there is no load or the load with infinite resistance. Then we place the voltage source UI across the input terminals and calculate the resulting current I and their ratio. It's not complicated. According to the KCL, the current is 101I. UI is equal to 515K times I. Ri is equal to Ui over I, which is equal to 515K ohms. Then we calculate its output resistance. The input voltage source should be deactivated, which means it's short. We short it, and we place a voltage source UO across the output terminals and calculate the resulting current I1 and their ratio. The current here is UO over 5K. The current here is UO over 10K. So I equals minus UO over 10K. By applying the KCL at this node, we get that 101I plus I1 is equal to UO over 5K. By substituting this expression into this equation, we get I1 is UO over 5K plus 101 UO over 10K. This part approximates to 50 over 5K. Then I1 approximates to 51 UO over 5K. So RO is equal to UO over I1, which is equal to 5K over 51, approximating to 100 ohms. Is this 515 kilo ohms input resistance large enough? Is this 100 ohm output resistance small enough? The answer is yes. Why? If we regard this as a voltage signal processing circuit, this is the input port and this is the output port. The circuit is a cascade connection of many signal processing circuits. The concept of the cascade connection is discussed in the lectures of the two-port network. If the input resistance of every two-port is 515K and the output resistance of every two-port is 100, the equivalent circuit seen from this port to the left and the right side respectively is like this. The 515K input resistance is large enough and the 100 output resistance is small enough to ensure that the voltage signal can be transmitted with little loss in the signal processing circuit. Next, we discuss another question. If the voltage signal processing circuit's output port is connected to a very small load resistance, whose value is 5 ohms, what's the input resistance in this condition? The parallel connection of 5K and 5 ohm is almost equivalent to 5 ohms, so we can ignore 5K ohms here. Similar to the derivation above, we place a voltage source UI across the input terminals. UI is equal to 10K times I plus 5 times 101I, which is approximate to 10K times I. Ri is equal to Ui over I, which is equal to 10K, much smaller than 515K. But in the cascade connection, the load is 5 ohms. See from here to the right, the input resistance is 10K. Seeing from here to the left, the output resistance is 100 ohms. Although 515K changes to 10K, it is still very large comparing to 100. It proves our previous discussion. When we discuss the input resistance of the voltage signal processing circuit, sometimes we should consider the load resistance, sometimes we needn't. So, in what condition should we consider the load resistance, and in what condition we needn't? Usually, if the input resistance of the voltage signal processing circuit is still relatively large comparing with the load resistance taken into account, we can ignore the influence of the load resistance. The following discussion is about the application of the actual voltage signals. Firstly, we need an input stage, which can sample and transmit a weak voltage signal with no distortion to the next stage. Secondly, we need an amplification stage, which can amplify the weak signal. Thirdly, we need a drive stage, which can use the signal to drive the load. These three stages have different functions. The input resistance of every stage is Ri1, Ri2, and Ri3. Similarly, the output resistance of every stage is Ro1, Ro2, and Ro3. Then we can get the case stage Thevenin equivalent circuit. It's a series connection of USK and the case stage output resistance ROK and the K plus 1 stage input resistance RIK plus 1. It's a voltage divider circuit. If the signal can be transmitted to the next stage with little loss, the input resistance of every stage should be as large as possible, and the output resistance of every stage should be as small as possible. Similarly, we can discuss the input and the output conductance in the current signal processing circuits. In the current divider circuits, the input conductance of every stage should be as large as possible, and the output conductance of every stage should be as small as possible. Thus, the current signal can be transmitted to the next stage with little loss.